In this module, we'll discuss where melts are generated on Earth and the relationship of those locations of melting to tectonic plate boundaries and why the crust and mantle melt. This table organizes locations where melting takes place in the mantle and crust based on whether you're in an orogenic setting or an anorogenic setting or somewhere in between. In the orogenic setting, we have oceanic island arcs, where oceanic crust that is older and colder and denser subducts beneath younger, more buoyant oceanic crust, creating a volcanic arc. A continental arc setting where oceanic crust subducts beneath a continent, or a continental collision setting like the Himalaya, where continental crust is subducting beneath other continental crust. In the anorogenic setting, we have continental rifting or hotspots within the continents, or mid-ocean ridges or oceanic islands where oceanic hotspots might form. And then we can have some transitional settings where we have a post-orogenic collapse that might generate some melting. I'll tell you a little bit more about these. The mid-ocean ridge system is by far the largest generator of melts. And this is where the oceanic crust is thinning along the plate boundary, and mantle is therefore coming closer to the surface, and the reduction in the pressure on the underlying mantle actually reduces the melting temperature of the mantle, generating partial melts of the mantle that are basalts and that come up at the mid-ocean ridges. To a lesser extent, we have basaltic melting beneath hotspots, and these locations are different hotspots either within oceanic plates or within continental plates. You'll recognize Hawaii and Yellowstone as hotspots that you're familiar with. There are many of them, and including some special situations like Iceland, where we've got hotspot volcanism taking place along the mid-ocean ridge. Now, hotspots are thought to derive from the core mantle boundary. So down here, where the solid lower mantle is in contact with the very hot core, it generates plumes that rise up because they're more buoyant, and they can generate volcanism within a plate. So there's no relationship necessarily to a plate boundary with a hotspot plume. And this diagram also illustrates the fact that the lower mantle is physically stratified from the upper mantle because it's a solid lower mantle, because of the great pressure at those great depths. And the upper mantle is chemically different too from the lower mantle, and it's thought that, well, I've just explained that the hotspot basalts are generated from this lower mantle, that mid-ocean ridge basalts are coming from the upper mantle. And so what this says, upper depleted mantle, is a source of the mid-ocean ridge basalts, and the lower undepleted and enriched mantle is a source for the oceanic island basalts. Those are the hotspot basalts. And so this depletion is a chemical depletion, whereby you're removing some of the trace elements in the uppermost mantle by partially melting the upper mantle, and the lower mantle remains relatively undepleted. And so it's more enriched in those trace elements for the hotspot basalts. Another area where you're probably familiar with magmatism is at continental arcs, probably because they end up generating spectacular eruptions. But the granites of the Sierra Nevada batholith are part of that system. Those are simply the lower parts of the arc that crystallize beneath the surface of the earth. And we also have volcanics associated with these arcs. So these are locations along the western coast of Chile and along the western coast of North America where we've had oceanic crust subducting beneath the continents to generate those melts. Now, I want to clear up a very common misconception about how melting works at continental arcs and subduction zones. Here's a schematic subduction zone where we have oceanic crust subducting beneath a continent. And what this diagram shows is there's the oceanic crust that's downgoing, and we have this purple mantle, and I'll call that the mantle wedge, because it forms a wedge-shaped area above the subducting slab and beneath the continent. And how melting works and where those magmas come from are the basaltic crust and lithospheric mantle of the oceanic crust are carrying down with them phyllosilicates like micas, clays, serpentine, and other hydrous minerals like amphiboles. So they have that hydroxyl in the mineral formulas that you have. That's structural water. And as these rocks are subducted, they're metamorphosed to higher and higher grade. And as those metamorphic reactions take place, they dehydrate those minerals. So those minerals lose their water, and they're metamorphosing and becoming different minerals, but they lose that structural water. That water is buoyant. It enters, just as these arrows suggest, it enters the mantle wedge. That water lowers the melting temperature of the mantle and allows the mantle to actually melt. So it's not the subducting slab that melts, it's this mantle wedge that is partially melting because of the addition of this water from the metamorphic reactions within the basaltic crust. Those partial melts are basaltic, and they're buoyant, and they rise up and then pond or penetrate the continental crust. And then they undergo a process of differentiation through a variety of means that I'll discuss in a different lecture to generate mostly andesitic type magmatism and volcanism in the continental arcs. So be clear on that. It is not the subducting slab that melts, but the mantle wedge. Another place we might get melting is in continent-continent plate boundaries, so continental collision zones. And in this example, we have Indian crust on the left subducting beneath Eurasian crust, or the crust of Tibet on the right. And again, we have metamorphic reactions taking place when you bury rocks to greater depths. And again, we have a process of dehydration of those same kinds of minerals, the phyllosilicates, the amphiboles, and those generate water because it's released from the crystal structure during the metamorphic reactions. That water then lowers the melting temperature of the continental crust in this case, and the partial melts of the continental crust are actually leucogranites. So where it says anatexis, that is the name of this process whereby you're generating fluids from metamorphic reactions and partially melting continental crust to get something called leucogranites. And this simply means that they are granites, but they're true granites, but they have very small amounts, less than 5% of the mafic minerals in the granites themselves. So barely any biotite or hornblende in them. So this is another process that you can generate melts. You can also find melting taking place or magmas being generated in continental rift zones. Here's an example of the East African rift, where there's a plate boundary that's trying to develop in Eastern Africa. And in those cases, we have thinning crust, where the continent is being faulted and stretched, like the Basin and Range province in the western U.S. You see a series of north-south ridges and valleys that form the Basin and Range. Areas where the crust is thinning, that also reduces the pressure on the underlying mantle and allows the mantle to melt. This has far too much text in it, but you can read that later if you like. But this is a model for how this decompression melting might work. You have a crust that is beginning to thin in the top diagram, where there's some stretching taking place and the continent is being pulled apart. You have normal faults being generated that help to help this thinning process take place. The underlying mantle down here is coming closer to Earth's surface. The pressure is reduced on it, and it's generating partial melts of the mantle here, and also generating basalts in those partial melts. And then, like when the partial melts of the mantle wedge in a subduction zone pond and intrude into the crust that lies above it, there's going to be a process of differentiation so that you can process those basalts and end up with a variety of different kinds of magmas and volcanics as a result. And so in this setting, you actually end up getting a bimodal volcanism. You get everything from basalts to andesites to rhyolites in a continental rift situation. This table has a lot of information, but I want you to focus on this area that I've just highlighted below. These are the same table at the very top that I showed you at the beginning. And what I want you to see is that the kind of volcanism or the magmas that are generated at each of these settings. So we have in an oceanic island setting, we're getting basalts and andesites. In a continental arc, andesites and dacites. Continental collisions, often there is no magmatism, but like in the Himalaya, we have anatexis taking place, and so leucogranite generation. In a continental rift situation, you'll get alkali lavas, so sodium, potassium-rich lavas. And in the mid-ocean ridge and oceanic islands like hotspot plumes, we get oceanic island basalts and mid-ocean ridge basalts. And as I said before, because the mantle is stratified physically and chemically, we have several different kinds of basalts that can be generated. And this diagram is showing you that you can use trace elements. Different examples here. These are called discrimination diagrams. But you can use trace elements to discriminate between or tell the difference between basalts that might otherwise are chemically very similar according to the major elements, but in the trace elements as I alluded to when I described the lower mantle being enriched and the upper mantle being depleted, the trace elements will tell us whether we are studying a mid-ocean ridge basalt, an ocean island alkali basalt. These are island arc tholeiites, oceanic island tholeiites, calc-alkaline basalts. So those will help us to further distinguish between similar kinds of melts and where they might have been generated. All right, what you learned was most melts are generated at active plate boundaries. Most are at the mid-ocean ridges. Second are melts generated at oceanic arcs, and everything else to a lesser extent in the continental rifts, in the hotspot volcanism, in the intraplate volcanism, and continental arc situations. The mantle wedge, not the subducting slab, melts in an arc setting. That the introduction of water that's released during metamorphic reactions, water that's released from internal structure of minerals in the phyllosilicates, the amphiboles, that enters the overlying rock and lowers the melting temperature of that rock and leads to melting, as in the Anatexis in the Himalaya, as in the mantle wedge in the subduction zone. That crustal thinning leads to decompression melting. So when you thin the crust in either a mid-ocean ridge or a continental rift, you are lowering the pressure on the underlying mantle, and that lowers the melting temperature of the mantle. Felsic rocks melt at lower temperatures than mafic rocks. That's why we're able to melt continental crust with small amounts of fluid in the Himalaya. And you should remember that the felsic minerals that are on Bowen's reaction series are crystallizing at lower temperatures than the mafic minerals. And if we turn that around, we can start to melt those felsic minerals, the quartz, the case bars, at lower temperatures than the mafic minerals like hornblende, the pyroxenes, olivine. Those melt at higher temperatures. The mantle is stratified both physically and chemically, and hotspots originate at the core mantle boundary. And trace elements can be used to distinguish the different types of basalts and to tell us whether we're looking at basalt that was generated in an oceanic island setting from enriched lower mantle, or whether we're looking at a mid-ocean ridge basalt that was generated from a depleted upper mantle.